In this lecture, we will talk about harmonic functions. So let me recall that if you have a domain in a complex plane and a function phi, which is, say, of class C2 in this domain, then we say that phi is harmonic if and only if it satisfies the Laplace equation like this. So this is the definition of harmonic. The theory of harmonic functions is very closely connected with the theory of analytic functions, and the reason for that is essentially that if you take the real part of an analytic function or the imaginary part, then these functions will be harmonic. You can talk about complex valued harmonic functions and real valued harmonic functions. In this case, you get a real valued harmonic function. And actually, this connection is even closer than that, because it turns out that if you have a real harmonic function phi, then it will be the real part of an analytic function. Perhaps that is not true in every domain, but it is true if you have a simply connected domain. So the idea behind that is that you simply define a function like this, given phi harmonic. Then you define a function g like this. You take the derivative with respect to x, and then minus I times the derivative with respect to y. Then it turns out that this function is analytic. In the given domain then. And the reason is simply that you can check the Cauchy-Riemann equations here now. So the first Cauchy-Riemann equation says that the x derivative of this should be equal to the y derivative of the imaginary part. And since you have a minus sign here, this will then be the y derivative of minus the y derivative of phi. And then you see that if you move this term over here and the minus sign outside, then you just have the Laplace equation. Then the second Cauchy-Riemann equation states that if you take the y derivative of this real part, then this should be equal to minus the x derivative of the imaginary part, which is this then. And now these two minus signs cancel, and you see that this is just the fact that the mixed second order derivatives equal for a C2 function. So we see that this is really an analytic function, and if the domain is simply connected, you can define a primitive analytic function like this. And it turns out that this function will then, up to a constant, be the one f which gives phi as its real part. You see, here you have taken the derivative, so to speak, of phi. And now we have integrated again to get an analytic function. And then it's not so strange that you will get back phi as the real part of capital G plus a constant. One consequence of this is that if you have a harmonic function phi and you compose it with a analytic function, then this composition will also be harmonic. Simply because if this is harmonic, then it's the real part of an analytic function. If you take that analytic function and compose with this analytic function, of course the composition of two analytic functions is analytic. And then you see that this is just the real part of that composition, which automatically is then harmonic. So in particular, this means that if you have a map, say f from, say, the unit circle onto some domain omega. So say you have conformal equivalence here. Then you see that whenever you have a harmonic function here, then if you call that phi, then the composition here will be a harmonic in U, in the unit disk. Which means that for many purposes you can really study harmonic functions in any omega which is conformally equivalent to the unit disk, just by, so to speak, moving the problem back to the unit disk then. And now we also have the Riemann mapping theorem, which says that if you just take any simply connected domain with the one exception of the whole complex plane, then it will be conformally equivalent to the unit disk. So there will be a map like this. So from now on, we will concentrate on harmonic functions in the unit disk. And to start with, let's suppose that we compare with the analytic situation. So let f be a function which is, say, analytic in a neighborhood of the closed unit disk. Then we have the Cauchy integral formula, which says that we can represent this function as the integral of f of zeta divided by zeta minus z d zeta, like this. So this gives the value of an analytic function at any interior point in the unit disk in terms of the values of the function at the boundary. So in a sense, this also already gives a representation for harmonic functions, because remember, if we have a harmonic function, then it will be the real part of an analytic function, and the analytic function can be represented in this way, and then we just take the real part of this expression, and then we have a representation, an integral formula for our harmonic function. However, that integral formula is not very practical to use for different reasons. So I'll now show how we can get a much better formula for harmonic functions. And the first observation we make is that if you consider the function f of zeta times z conjugate divided by 1 minus zeta times z conjugate, then this function is certainly an analytic function of zeta, which then means that if you integrate it along the boundary of the unit disk, this will this integral will be 0. So this, of course, is true as long as the absolute value of z is less than 1, as it is in the unit disk, because then this function here will have no 0 in the unit disk. Okay, so once we know that this integral is equal to 0, we can simply add this integral to what we have here. we can multiply by 1 over 2 pi I, and then add this integral to this, and still get a formula for f, which will then be integral over the boundary here now, and then from here we get the factor 1 over zeta minus z, and then times f of zeta, d zeta. And then from here we'll get plus zeta, z conjugate divided by 1 minus zeta times z conjugate. So this is still an expression for, an integral expression for f of z. And so what we do now is simply to rewrite this integral in a nicer form. So we put these two expressions on a common denominator. So here we, on this denominator, we'll get 1 minus zeta times z conjugate. And here we will get plus z conjugate times this expression, which is then zeta minus z. And then we have the f of zeta d zeta here. And now we observe that this term here will cancel out against that one. And so what we're really left with in the numerator will be 1 minus z conjugate times z. So it will be 1 minus z absolute square. And so what do we get down here? Well, just leave it like this for the moment. So in order to rewrite this in a better form, we have to now parameterize the unit circle, which we do as usual by putting zeta equal to e to the I t, like this. And then we see that this integral can be then be written as 2 pi I times 1 minus z absolute squared, you know. And then we get down here e to the I t minus z times 1 minus e to the I t times z conjugate. And then we have f of e to the I t. And then we have the differential of this, which will then be I times e to the I t dt, like this. Now, to simplify this further, we first note that the i's will cancel out here now, and then we can move this factor e to the it down in the denominator, and then we'll get that we have to multiply down here by e to the minus it, which will then give us the following. So we'll get, I multiply this factor by e to the minus it. And then we'll get e to the it minus z. And here we'll get e to the minus it minus z conjugate. And then we have f of the e to the it dt. And what we see now is that this expression in the denominator is actually real. So everything in this integral has become real now. The reason why this is real is that if you take the complex conjugate of this expression, you get exactly this. The conjugate of e to the it is e to the minus it, and the conjugate of z is of course minus z. So this is actually equal to the absolute value of e to the it minus z squared then. Of course, this way of writing it is perhaps not the nicest form either. Once you've left the complex notation, you can do away with this also. So, here we should have write this as an integral from 0 to 2 pi now when we have parameterized. And so we have here from 1 over 2 pi times the integral from 0 to 2 pi of, and if we now write z in polar form, like r to the e, r times e to the power I theta then we see that up here we get 1 minus r square. And if you just compute this product down here, you see that this times this will be 1. This times this will give you r square. And the cross terms here now will actually turn out to be real then. And what you get is just minus 2r times the cosine of t minus theta. Like this. And then you have this function f on the boundary. So what we have here now can be called the Poisson formula. And in a way it can be said, this Poisson formula can be said to do the same job as the Cauchy integral theorem, because what we actually shown is that we can represent our analytic function inside the unit circle by an integral like this. However, since this part now is completely real, we see that if we just take the real part of the left-hand side, which is our harmonic function phi, say then that will be equal to the real part of this expression. And since only this part is complex now, you see that you get exactly phi represented in terms of a real integral of phi itself. Okay, so if we sum up now, what we have is, if we have a harmonic function in the unit disk, then we can write the value at the point inside the unit disk. And now I use the real notation, so I write the coordinates for the point in this way. And this will be equal to the integral we have from 0 to 2 pi of 1 minus r squared divided by 1 plus r squared minus 2r times the cosine of theta minus t, or t minus theta, doesn't matter. And then we have the function f at what the function phi at the point what I before wrote as e to the it, but now I simply write it as in the real notation in this way. There should be a t here. Like that. This gives the value of the harmonic function at any interior point in terms of this integral, which then uses only the values of phi at the boundary. What is interesting is that if you just start with essentially any function, well, let's say for simplicity that it's continuous. If you just start with any continuous function on the boundary, this integral formula will give you a function inside which actually always turns out to be harmonic, which you can see then simply by differentiating this under the integral sign. So this is now a formula which is very useful in real analysis, for example in potential theory. But of course, if you want, you can also use it to represent analytic functions. So if this is a formula which is true, so to speak, both for the real part and for the imaginary part, so if you prefer the complex notation, then you can write this function, this analytic function, as 1 over 2 pi times the integral from 0 to 2 pi of this function, which we can call P of R theta and T, which is called the Poisson kernel then, and then times F of e to the I t and then dt like this. And then we also have the Cauchy integral formula, which then can be written in this way, the one we started from then. So both these formulas, they give you a way of representing an analytic function inside the unit disk in terms of the values of the analytic function on the boundary of the unit disk. So are these formulas then perfectly equivalent then? Well, the answer is no, and you can see the difference here now when you try to apply them to a situation where the function is not analytic inside. So what happens with the Cauchy formula here now, if you try to evaluate it with a function f given on the boundary, but which is not analytic inside? Let's suppose that it's have some pole or something. Well, this integral will still be analytic as a function of z. But what happens is that it will no longer agree with the given function here now. Because the given function was not analytic, and this one is, so they cannot really agree. But what happens if you use the Poisson formula instead? Well, the thing is that the Poisson formula will always reproduce a function as it turns out, which is harmonic, and it will agree with a given function on the boundary. If you take this expression and let r approach 1, you will get exactly the value that you had assigned at the boundary before. But what happens here now is that if this is not the boundaries of the boundary values of an analytic function, this function will only be harmonic, but it will not be analytic. So the real part will be harmonic and the imaginary part will be harmonic, but they will not fit together to an analytic function.